All right. All right, let's everybody get their seats. We'll get going here. Thank you very much. All right, welcome to the SpectrumX Flagship overview session. I'm Frank Lynn from MIT Haystack Observatory. We're going to have a little bit of an introduction from Nick. Then you're going to hear me give you an overview of our flagship projects. That's going to take a good chunk of the time because we're doing a lot, as you'll see. And then we're going to have presentation questions and answers, so things about the presentation, things we're doing with the flagships. We'll try to shoehorn Mike and Nick and Scott to come up here with me, so it isn't just me answering all the questions. It'll be more interesting. And then, at the last 15 minutes in here, I think that what we'd really like to have is a discussion of complementary efforts and projects. Things, we're not aware of everything in the world of Spectrum because I don't think that's possible for anyone to do that. But there's a lot of ongoing things our flagships are relevant to, and I'd like to talk about opportunities to engage outside of the center and also to leverage things and capabilities that we might not have been considering in how we structured things. So with that, I'll give you Nick.
All right, good morning again, and thank you everyone for sitting in this session. It's an important one to SpectrumX, and it's really an outgrowth of a couple of years of operating as this National Center for Wireless Spectrum Research, engaging with the community, getting feedback from NSF review panels, and trying to focus our efforts. So that's a key word here. We're trying to take our research enterprise, focus it, make sure that it's more policy relevant, and ideally creating policy impact in what we do. Because we have a big center, we can potentially scale some things up and have a lot of impact. And we're really grateful that this past year we've started to focus around this notion of flagship projects. And Frank has joined as Deputy Research Director to help with some of the efforts that Mike Honig has been leading. And so Frank and Mike and Scott and I are really, really putting a lot of energy into trying to structure this project activity so that we can get the kind of relevance and impact that we want to see for SpectrumX. So it's important that we present these ideas to the community. So thank you, Frank. It's also really important that we get feedback from the community to make sure that we keep focusing and we keep avoiding duplication of efforts, but actually generate some of the impact that we can potentially create. With that, back to you, Frank. Thank you.
Right. Thank you very much, Nick. So I'll be talking to you about the flagships today, and underneath this is an effort that we're going to try to pivot our research to for the next few years. But SpectrumX is made up of people when you get down to it. We have such a wonderful team of people across so many institutions. Actually, the thing that made me want to do this and take on this effort of kind of trying to get everybody to sing a common song is that I've enjoyed so much my interactions and some of the cross-disciplinary stuff that's come out of the center that never would have existed. I come out of a geospace radar, astronomy, space plasma physics, spacecraft background. I've done a lot of stuff in radio over the years in software radio and software radar. And this is, for me, kind of a pivot into a much wider world that had existed in parallel to a lot of the things that I'd been doing. So I'm really enthused about this opportunity to help lead this and to help bring the team together. And I have to acknowledge the contribution is we had a workshop at Haystack. We had a lot of people from SpectrumX join. And this isn't just stuff I put together wholesale out of whole cloth. I took so many contributions and comments from people, and I just want to acknowledge everyone who really brought things to this. So we're looking at creating flagship projects, which we think of as significant center level investments. And initially it looks like we can support kind of one major one and one what I would call medium scale one, and I'll talk about those. And we have a research planning committee that weighed in on this when this idea came up of kind of focusing our research in some meaningful directions for the near term. And out of that came the idea that we would do some mid-band science, a mid-band oriented flagship and a science oriented flagship. And this was at the time we should do something, right? And I've tried to take it with the help of everyone into something where we have a much more focused project and project plan. We took a workshop-based approach to formulation, and this has happened for our first flagship, which I'll talk about on spectrum awareness. But the second flagship, we're going to be having a workshop at some time, probably a little later in the spring here, as we need to dodge school schedules and everybody's vacations and everything. But we're going to get that going. And I'll talk about where that project is conceptually at the end. These are going to be formally managed projects. Tomorrow we're going to have a session that you're welcome to come to that's going to talk about the details of the flagships and our structural organization and the project management. It's kind of the inside baseball. And we're going to have a project manager, Mary Knapp from MIT Haystack Observatory. She's actually a really esteemed scientist, but she does a lot of satellite-based project management and activities and has worked with us on some important missions. And she's going to be joining us to help us organize and schedule and plan and keep track of what we're doing. So this is a little different than just the herd of academics running around. Not everybody's used to this framework. So we're going to be working to keep the managerial aspect lightweight, but to keep it effective on keeping to milestones, keeping on task, and trying to get the most out of our resources. We are looking to generate explicit policy relevance in every flagship and also potential impact. We would love to have explicit policy impact, but I can't guarantee that. That involves other people in the world adopting the things and the ideas that we put forward. But we are going to position what we do very carefully to maximize the chance of such impacts occurring. These are going to be near-term results. So near-term to me here means 2 years, roughly. That's about the time we have to execute this. We're hoping to have meaningful results well within the next year. And then there are some areas that you'll see that are clearly going to take more resources and be sustained efforts over longer terms. And these will kind of be obvious when they show up. They tend to be things that take a lot of infrastructure investment, either in the development of systems or circuits or in the development of softwares and algorithms, for example. And those higher, longer term things are ultimately going to result probably in proposals to other agencies and opportunities in an attempt to leverage other relationships in order to build the needed effort necessary to realize the full vision that might be possible for those areas. So examples of policy relevance and impact. Well, what do I mean by that? You can have models, for example, that enable improved spectrum prediction and predict coexistence behaviors. You can have sensors that might enable us to efficiently measure the environment and collect relevant measurements in a band. You can have systems and technology that address societal problems or show how to be resilient to perturbations or bad actors or things that might happen where it might be advantageous to coexist in a way that say provides a backup to GPS or a backup to time synchronization services. Now, policy impact is a little different thing. This is, at a high level, it's to inform or educate regulators and potentially politicians in a useful manner. You can have studies, for example, such as the National Spectrum Strategy, which I'll get back to in a second, that help address topics. And so, we can target things like that. You can have models, analysis, or data specific to responses such as NPRMs. Or you can work to, look at coexistence and participate in these areas, such as the ITU and the WRC 27 topics. So there's areas, you can have an impact, and SpectrumX has been working to have additional impacts to contribute in these areas. And on the flagship level, we can ensure that our flagship work has policy relevance. We're going to target it at having policy impact, and hopefully the aggregate result will be very effective. So flagship 1, as we've called it for a long time, is focusing on spectrum awareness. And what we're, if we're really thinking about this at a high level, what we want to do is enable next generation sensing, awareness, and understanding at scale. Now, our initial budget and resources and effort, although generous, is not really sufficient to do this at a large scale. We're not Google. We're not going to roll it out across the country. We have to focus. And to focus, what we're going to do is we're going to be looking at the 7 to 8.4 gigahertz band that's relevant to the national spectrum strategy. And there's a lot of SATCOM in this band. I've got the eye chart up here of, this is actually a beautiful piece of graphics, by the way. This is, the people who put this together originally and who have involved it, it's like, it's actually like really attractive and, for those who like spectrum and get to know it. But the, underneath, there's a lot of users in this band, a lot of government use. In particular, there's a lot of satellite communications, uplink and downlink. NASA and NOAA do this, the DoD does this. And we're actually going to be focusing more on the NASA NOAA SATCOM side. I'll talk about that in maybe the questions and answers if people want the rationale for that. But everything we do should be very relevant and transferable. It's just that we had to pick a very specific thing to focus on. And what we hope to do is create a demonstration of the possible for coexistence. And we want to do this by combining the different talents in our centers and efforts and getting everyone to focus in on asking questions and answering questions about coexistence in this band. So for example, we've got sensors. We've been working on a variety of sensors. We're going to be taking some of the things that have really worked for us and scaling them out and using them. We're going to be taking some of the things that need additional development and focusing them into areas that nobody else is doing. And then we're going to couple that into the AI, for example. I've asked everyone to answer really, really complicated questions like, are we seeing the sky? Are we indoors and outdoors, right? It sounds very easy, but it's actually pretty hard when you're running radios. And there's a certain aspect of making the radios detect interesting things, right? You got to detect when something's in the band that you're not interested in. So we're going to be working to try to do development of that. We're going to be working to try to visualize this. This is all going to be organized around training and field experiments. So we really have to get the education and workforce development into this. And the key aspect from this, from my point of view, is getting students building radios, taking them in the field, doing measurements, learning how to calibrate things, learning then how to take the data, analyze it, and reach closure on making conclusions and understanding what's in that information they've collected. And so you're going to see in a second that we're really focusing Flagship 1 around experiments. Now, that doesn't mean we're not going to have modeling and policy effort. It doesn't mean that those efforts, I'm asking for predictions that are testable, which is a little hard. We may even do some wargaming, and Mike hates this term, but we're going to do wargaming to explore different regimes of policies and rights and try to do some really interesting things to understand that, along with the economics of what might be involved in some of the decisions we might look at for coexistence in this band. And finally, at the end of this, we're going to be developing these concepts and capabilities and infrastructure, and they're going to be deployable and transferable to other areas. So for example, if later we want to go, or during this timeline with resources, we wanted to go and do an experiment at an NRDZ, we could go do that, all right? And so there's this aspect of what's different about what we're going to do versus what an NRDZ might do. Well, an NRDZ is a certain infrastructure in a certain location with certain capabilities. We're going to bring certain capabilities to any location where we want to do experiments. And it's very complementary. All right. Types of spectrum awareness. What does this mean? Okay, you'll see this in the spectrum awareness. I didn't invent the term. It's out in the literature. I'd appreciate actually if somebody knows who's the first person who came up with this as an idea, kind of. But underneath it, I think there are many different types of spectrum awareness, of understanding what's happening with our electromagnetic environment. One of them is policy-driven, okay? And I call this policy-driven. It's a set of choices people make and say, this is how we want to use spectrum. It's how we intend to use it. We just saw a wonderful talk talking about this in the United Kingdom and how they have kind of a little different approach to it than we do, but it's solving the same kinds of problems. And then it's all in an international framework, of course, so there's a time scale to policy-driven spectrum awareness that's very long. And if actors are doing something, people are doing something in an environment in one of these bands that we allocate to a specific purpose that's not what we intended, well, then we talk about, enforcement and legal options and whether we can actually tell that that is happening. So that's one kind of spectrum awareness. You also can have model-based spectrum awareness. For example, on the right is a little service you can go to. It's called TV Fool. I don't know who put it together. It's on the web. You can go put in your location and get a estimated power map of say, a television station at your location, and they probably make some click-through revenue from this. It hasn't developed much in quite a long time, but at the base level, we have lots of little models everywhere that do this. There's ITS maintains probably the best of them, but nevertheless, there's a good set of modeling associated with this. There's lots of unsolved modeling problems. Models can tell you what you should expect to see in the spectrum. If I ask, go on top of this building and ask, how strong are the FM radio stations and which should be the strongest? A model can give me that information. So that's another piece of spectrum awareness. You can have data-driven spectrum awareness. You can go out and you can measure with your sensors and drive around, and you can make a heat map. And the Notre Dame team has done a lot of this with Radio Hound in real time. Actually, Bert was showing us earlier some very interesting stuff they were doing, triggering things based on events and and using sensors in a coordinated fashion to do data-driven spectrum awareness. And then you can also have real-time spectrum awareness. You can have a radio or a device. You can actually go to these. These are Kiwi SDRs. You can go look them up. And you can bring up these radios and watch them stream in real time and click on them and understand in the moment what is happening in a particular location, in a particular band in the radio spectrum. Now, these are HF-oriented, but we can imagine this on a much larger scale. And at the the visionary level, you can combine these things together ultimately into kind of the equivalent of the National Weather Service. You can have the equivalent a National Spectrum Service that assimilates information, model, data, predictions, and tells you, generates a nowcast and a forecast of what the electromagnetic environment around us should look like and does look like, and what we think it might look like in the near term. So that's maybe the long-term vision for this, but can we achieve quantitative spectrum awareness for a specific set of experiments? So what we're trying to do is organize ourselves to do this and to answer that question. And in the near term, what we're doing is we're developing policy scenarios and experimental platforms. All right, those experimental platforms are based on existing things that we've done at MIT. It actually was an RU project that was associated with SpectrumX that actually was very successful. And it wasn't the project I'd set out to do. I'd set out to do something I called the Great Haystack RFI Hunt. And what it turned into was building the platform to enable such a thing. But we're going to leverage that and some of the other things we've done and integrate it over the next actually probably 6 to 7 months into what we call the mobile experiment platform. And this will have transmit and receive capability. We're going to do some block up down conversion to get low cost software radios into the 7 to 8 gigahertz band. And we're going to then do a very interesting thing with this is we're going to have a workshop at Haystack where we bring the students and we're going to have them build these and put them together and do an experiment. All right, so there'll be teams. I'm hoping to build about 10 of these and maybe have 2 to 3 students per unit from a given organization. And they're going to take these mobile experiment platforms, learn how they work, learn how to put them together, and use them at MIT Haystack to do the first experiment. And this is the training experiment. We want to do it somewhere, quote, safe, right? Where the training wheels don't have bigger consequences. We're then going to send the students home with those to use them, and there'll be some competitions, I think, for signature collection for the AI/ML. There'll be some things they can do with them between field experiments. So that's the build your own radio platform, and we're hoping for that kind of around the end of the year here. January at Haystack is probably not the best time actually to have this, but nevertheless we'll make do. We can always do indoor outdoor, right? You run outside, you get really cold because it's snowing and 3 feet of snow is on the ground, and then you run back inside and see what the inside propagation looks like. Our hope is that about a year from now, we'll be able to engage in something that will likely be with NSF's, a little bit of NSF guidance with NRAO, and that would be a 7 to 8 gigahertz coexistence experiment. And I look at this as playing red team, okay? So we go to NRAO facilities, we do a coordinated coexistence experiment, and we pretend to be Wi-Fi. We pretend to be point-to-point wireless. We pretend to, maybe be fixed cellular at a little higher power level. If anybody's got a cell on wheels for 7 to 8 gigahertz, we could borrow. I'd kind of like that, but nevertheless. And then we could actually do these field experiments and evaluate the impacts, for example, on the radio telescope. And that's a training experiment. It's not going to be the most complicated. We don't expect the modeling to be as far along at that point. We don't expect our prediction capabilities to be as far along. But nevertheless, it'll be a very good experience for all the students, and it should get us some very interesting quantitative data about how very large and sensitive telescope systems respond to signals in these bands. We're also going to be working on an adaptive array demonstrator that I'm hoping we can have ready for what I think of as our major flagship experiment, which will happen in a couple years. And that major experiment is going to be focused, I hope, around coexistence with a real NOAA NASA facility complex. And I have in particular in mind trying to do this at Wallops Flight Facility. I have to talk to everybody about this. We have to reach out a little bit to NASA and NOAA. I actually, strangely enough, know all the people at the low level at the NASA and NOAA facilities, but I'm going to need to engage with some of the upper management to get permission to do this type of activity. And there's going to be a long negotiation process, planning process, and licensing process to get there. Nevertheless, we're hoping to actually have some of our advanced instrumentation for this. We're hoping to go and do things, for example, in terms of vision. What might we do? We might actually, for example, have them download data from a GO satellite, for example, and then do it again. Where they might repeat that block 4 hours later. We might have them do it more, immediately, where we then get to try to pretend to be Wi-Fi, pretend to be point-to-point wireless, examine the distances at which interference that's noticeable to them occurs. So there's the active experiment part of this that also we will couple into our policy rights wargaming. So we will go through and systematically try some really key scenarios where we can predict that there should be effects. And we may throw a few things in there. I've got some ideas for some really clever things we could throw in the experiments that'll be monkey wrenches for the students to adapt to. But it'll be a really fun experiment for everyone, and it'll be a pretty sustained effort. The other reason I'm thinking about NASA Wallops is their experimental team for doing rockets is absolutely first rate. They're an unbelievable team of people. And having that kind of logistical support is absolutely incredibly valuable to something like this. So, and then of course we're going to analyze this, and there's going to be a report, right? But there's also going to be papers. There's going to be a raising of awareness of these issues. We're looking a little bit at whether we can support some summarization of these materials for policymakers, for example. And ultimately this is going to be about next generation wireless in 7 to 8 gigahertz. It's going to come out right as all the government studies are going to come out, and there's probably a lot of room to coordinate with the government studies that are going to be planned to maximize the benefit of both of them. And so that's the overall big picture on this. And I can go through some key efforts. We have particular elements. One of them I'll highlight is RadioHound X. This is our next generation integrated radio platform. We're building on things we've done at Notre Dame and at MIT to try to unify this down into ultimately ASICs. So we're going to build an incredibly integrated platform, and then we're going to take it to the chip level. And we're not going to do this all within center resources. The students are going to start on some of these ASICs as prototypes. We're going to have to go out and leverage other opportunities to grow this area. But at the end of the day, we'd really like to see you able to go onto Amazon and click and get a 100 megahertz to 18 gigahertz sensor for, I don't know, it won't be $29.95, but it'll be less than you might pay right now. And they're going to be as integrated as we can make them with calibration and coherence, and a lot of capabilities I think will be very exciting to people. And that availability will enable something I think of as drop and go sensors. It's the future of spectrum sensing. Every fence post in America can have a spectrum sensor. We're going to do modeling, rights and policy analysis and economic analysis. It's going to be targeted at looking at novel policy and rights approaches for 7 to 8.4 gigahertz. We're really going to work to try to get these so that they make predictions that we can go test experimentally. So it won't be every model you can come up with. There's plenty of stuff that I know that Mike and Ilya and others can do that has analytical aspects to it or agent-based modeling aspects to it. We're going to try to get this into something where we pick the things that are more testable. Experiments, demonstrations, I've gone over those in quite a bit of detail. These are going to be just really foundational, exciting experiences for our students to build real knowledge about how to work with radio in the field, and I think it will change a lot of them for the good for the longer term. And then underneath this, we're going to need some data infrastructure, some Spectrum data system, a Spectrum sensor platform. These are leveraging a lot of efforts that have been nascent or ongoing. They're leveraging actually some efforts from outside the SpectrumX community that I've been involved in. And we're going to try to get this so that we've got good data, high quality metadata, and that all of this is available online as output. And so there's going to be an openness to these projects that I think is going to be a wonderful thing for SpectrumX, and it'll also be an enabling thing for the larger community. It'll reduce the friction for people understanding what we're doing, accessing it, and getting value from it for themselves. So measurement platforms, I talked about the mobile experiment platform in RadioHound. The existing mobile experiment platform is up in the upper right. We use it for field surveys at Haystack. The next one's going to be smaller, better. It's going to have GPU, Jetson Orin most likely. And it's going to be able to do some really, really wonderful spectrum things. RadioHound X, we're going to be building around a integrated Xilinx system and package that's available. It's an extremely integrated thing to start with. And then, as I said, we're going to have Sudhakar leading probably to look at building some of the ASICs for us. Data infrastructure and interfaces. We're going to be building on a geospace data system that came out of the atmospheric and upper atmosphere science community. And we're going to be using this as an architectural template so that we're not redesigning it from scratch. But the idea is that it's a federated architecture. You as an individual can go download this, build your own site, put your own data on it. And yet, you can link into the larger network and do global search. And we are going to have things like access control. So, if NTIA wants to run one of these and have it be closed and internal, they can make that happen, or they can have certain things available and certain things not. And we'll be able to accept batch and messaging inputs from sensors and models. So models and sensors data go in the same place, so they're easy to bring together and compare. And down the road, we may even be able to run models. The actual system we're utilizing as an architectural template runs models when the metadata exists or the data exists for the model inputs in parallel, and it'll present it to you in parallel with the outputs. Now, the visualization on the current system could be better, so we're going to do a good job of building visualizations, of getting, hopefully, I'd like to have a student competition for the best visualization every quarter or year or something. We'll work it out. And then, there's going to be some basic standard data systems formats, but it's going to be plug-in based. We'll be able to handle multiple data formats, multiple metadata formats. There will be another one. There is one I don't know about. So we're going to be able to make sure that happens. The Spectrum Sensor platform, that's going to be messaging controlled. It's a unification of Notre Dame's approaches and MIT's approaches to really build a powerful system for dynamic real-time messaging control of software radios in the field. This gets towards one of Nick's visions, which is of having networks of these providing application level value to the larger world, where it's not just one sensor, it's networks of sensors, and it's not just point measurements, it's aggregate effects, and you can model and do things at a network level that would be much more interesting than you could do individually, purely with manual control. And there will be kind of edge visualization to go with that, so we know what the sensors are doing. Our models and economics, rights, and policy here, we really want to do stuff that has testable outputs. We're going to develop tools, hopefully, to help us predict and analyze experimental measurements. And we want plans, experimental plans for these experiments that are guided by the testing of these policy and rights predictions. All right, so this is going to go very strongly into the experiment planning process. Every experiment we do is going to have a written plan. It's going to have who's going to do what, what's going to be done, why are we doing it, how do we expect to evaluate the data that's taken, how are we going to analyze it, what are we going to put together on it, and then what question are we going to answer, right? That's good science. It's model the data, take data, then compare and understand what you did and what the results really are. This is going to unify in this report in a couple years, and it should be very well tied to the National Spectrum Strategy and its implementation plan. And I hope very innovative and novel. We've got a wonderful team of very bright people, and I think there's an opportunity for such contribution across the board. And it's not going to just be one person writing this report. We're going to do kind of a mini National Academy process internally, right, where we write the thing and then we review it internally, and then finally it'll get published. Experiments, I talked about these. We can leverage MIT Haystack Observatory as our initial test bed and training bed for this. This is up in Westford, Massachusetts. We're a laboratory of MIT. It really is named for looking for needles in haystacks. There's a long story behind that I won't tell right now. But nevertheless, we have both high-power radar assets, distributed sensor assets, radio astronomy telescopes, and we're coexisting already in a very challenging radio environment just outside of Boston. And so that's where we're going to cut our teeth and train the students. And down the road we may be able to have more than one training workshop, but I'm focused on one right now. And it'll be mostly graduate students. Probably their advisors need to be trained too, and probably some undergraduates who are maybe the more senior undergraduates or who can be involved given their class schedules and responsibilities. I see us playing red team with NRAO for some of these experiments. I see us working with NOAA and NASA. And the end of these experiments is really to get a radio and field experiment capable workforce. There are those in the audience who recognize that they were asking for this, and I'm trying to make sure we take steps towards delivering it. Underneath, next generation wireless and 7 to 8.4 gigahertz ties to policy. We want to have focused model experiment comparisons, largely SATCOM focused, but we want to evaluate this matrix of policy and rights use cases and deliver a really novel and independent band study. And the science we're going to do, the data we collect, we're going to make available, and it's going to be very relevant, I think, both to this initial spectrum question we have, but also to our ability to have best practices, open documentation, and data sharing for answering future spectrum questions. Because 784 is not the last one. It's just one we picked out of many. Now, Flagship 2. Flagship 2 is very much in preview and formulation, and underneath it, the one line for this is looking up and looking down. Mega constellations, the move of cellular into K-band, all of these things are creating a radio environment that for scientific instruments, the passive services as we call them, is incredibly challenging. The sky, astronomy benefited greatly from early access to the radio spectrum. We were there first with radio telescopes that were sensitive because there were very few people with enough resources and a challenge that they met to observe the larger universe. And so it was the undiscovered country, it was the wilderness. of radio, and you could go out and you could make observations that no one was going to transmit because no one could. All right. That era has gone away. We are at the end of it, unfortunately. So we have to look at coexistence, and that's ultimately based on good communications with people. It's about understanding quantitatively what really is needed to protect, say, a radio telescope or a weather radiometer. It's understanding that, there are really physical limits to the instrumentation we can build, and some of the signatures we measure astronomically or with, for hurricane forecasting are really incredibly weak compared to communication signals at a level that most people don't understand how many orders of magnitude there are, but it usually starts at 10 orders of magnitude of difference and goes up from there up to 200 plus orders of magnitude, or 20 plus orders of magnitude. So these signatures of satellites, of course, are problematic because they have such wide global distribution and visibility. A satellite from a radio telescope like an NGA VLA telescope is going to be visible for 2,000 to 3,000 kilometers around the site of the telescope. And it's not just the in-band emissions that can matter, it's how they affect the receivers. And so I see us having to model this very, very accurately, have validation of the models. I see us having to communicate these things much more clearly on a larger global scale. And in particular, we're going to try to address and tie into questions associated with ITUR and the WRC 27 process. So there's the tie into the policy inputs into WRC 27 as the timeline. But at the end of the day, we have to actually quantitatively understand in a very realistic manner these effects. And then we can start to ask questions about how we might do mitigation, how we might do coordination. And so we'll be looking at prototyping some of those approaches and maybe doing some interesting demonstrations that I've got in mind. So, and the team, of course, is the important part for this, right? And we're building the team. I've talked to a number of people who are quite enthusiastic about scientific coexistence. But if you're in SpectrumX or even outside SpectrumX and you're interested in this, talk to us. Give us input on this one. Give us input on Flagship 1, but Flagship 1's rolling. So there's maybe less perturbation that's possible there. But in any case, that's the larger view. So with that, we're going to go over to summary questions and discussions. I just say that our flagship projects are very exciting. Spectrum awareness is a real effort. We're putting a lot of resources into it, and we're bringing together the talents of just some really wonderfully talented people across the center. And this is going to go together into some very interesting experiences, field experiments, and then hopefully some very relevant policy input into the overall process, as Mike would like to call it. So thank you very much, and I look forward to your questions here. Scott, Nick, Mike, you guys can come up. We can field this. Are you guys' mics working?
Frank, thank you very much. It seems like a really robust approach to spectral awareness. Could you comment on, and I imagine this might come over time, what are your aspirations in terms of the real-time nature of the awareness? And how might that grow over time?
Near term, very limited. There's a limit to what we can do, although there are already some capabilities. I mean, we're going to leverage, for example, some of the heat mapping stuff that RadioOut's done that does happen in real time. So there will be non-zero aspects to that. I think the first Haystack experiment, for example, will have very immediate real-time awareness on the platform, so at the edge, right? The more centralized awareness of feeding into data infrastructure will be nascent. I think we'll be finding the bugs as that happens. I think that later, I think that we will have much more for those later field experiments. And longer term, of course, you want all this to be real time and very, very, very capable. And that's, for example, one reason for AI at the edge is to ensure that you don't have to exfiltrate all the data. You try to exfiltrate the really interesting data. So I don't know if any of you guys have a comment on that.
I mean, I'm in agreement. It's sort of the crawl, walk, run approach, and I think aspirationally, absolutely, we'd like to see this have a real time aspect. I think we've got to think through the process of getting there, and I think as Frank's laid out, there are some things we can do immediately, but to get to that sort of more global answer is going to take some time.
Other questions? That was a good warm up.
Let me just mention, I think in a local context, you can have, increasing real time. And then as you go, to larger and larger scales, I think you're going to see, less frequent updates. But we have demos now. It's something like 25 sensors in a lab, and the update rate is, let's say, a heat map of what the spectral activity in a room is a couple times a second. Is that?
7, 8 frames a second, yeah.
Okay.
And I realize it takes time to build. I'm just curious if you have targets that you would, aspire to. That was a great answer. Thank you.
Other questions? Renee?
I really appreciate that super helpful overview of basically both of really the overall efforts. And I don't think this is the case, but I wish that there were some NOAA and NASA people in the room, particularly about the 7 to 8.4, because I'm quite aware of some of the studies that they're doing as agency-wide in terms of being able to look specifically at 7 to 8.4. And actually, I was just speaking to Michael Morgan, who is basically the Assistant Secretary of Commerce for basically Earth observation and prediction yesterday, specifically about some of our discussions about Flagship 2 yesterday, and he says, we are all in and very much interested. And so I'm super happy about that. However, I think going back to Flagship 1 and talking about your ideas specifically about wallops, I think that's great. And I know all of the people in the frame who can sort of help to get all of the check boxes. So happy to help with that.
Thank you. This is an example of the power of the center, because of course Renee is part of our center, and so I think that's exactly what we need to now do. We put things together. We're getting the team rolling. The next thing from the larger experimental point of view is engaging the stakeholders very clearly and starting to build this permission process, starting to build trust. And then get to the point that we really can do something together, and it will become more than the sum of the parts at the end.
I'm ready to facilitate in the next few weeks. So,
Awesome.
yeah.
Thank you.
So this is probably a little more specific question about the second project, which you said
Okay.
is a little nascent right now. But you specifically say on this slide, address ITUR WRC 27. There's obviously a lot of agenda items, specifically on satellite issues on the agenda for WRC 27. And we've got a very aggressive timeline that's been laid out by the CPM to get parameters into the various working groups no later than the middle of next year. And it seems like this is going to be informative of that first step rather than perhaps some of the
I think
studies
there
that
will
follow,
be, there's already several things ongoing with the center that are really going to be able to feed into that. There's aspects of this that are quite a ways along, and I've talked to some of the other people doing modeling, for example, of this, that we're doing this kind of modeling for some of our sensors and experiments at Haystack that I talked about earlier in the week. But so there's stuff that's going on that I think will be more immediate inputs. And I know that Ashley at NSF reached out to me already about, hey, you guys were doing this and I saw this, could you actually contribute to this? So I think there will be kind of direct contributions. I think this is also about building the capacity to answer questions like this really effectively, both in terms of the people and in terms of the tools. Right now, if you ask me for any given radio astronomy receiver and any given satellite that you choose to put in orbit, people choose to license and put in orbit, are they going to have a problem, right? Well, it's an analysis to do that, and it's not necessarily always trivial. And the moment it's a satellite constellation, now we're having to sum over all the orbits and the side lobes, and we've done a lot of the work to make that possible, but putting it together into something where it's robust, also along with, well, okay, that's great. We know that you can't now use the radio telescope when that transmitter's on. What are you going to do about it? Right? And that's the hard question, because at the end of the day, you need resilience and overcapacity for satellite providers to actually, say, turn off in a band that NRAO wants to do an observation with NGVLA in. And that's something that right now isn't there. There's certainly a willingness to talk, but there's got to be societal incentives to get people to do that, or rules, governance, as it was discussed yesterday. So I don't know if you guys, Nick, you've got input on
Well,
that.
just as a point of order, if you don't mind introducing yourself
Oh,
before
yeah,
you
yeah,
answer.
sorry.
Sorry, I'm Dan Manser with Apple.
Sorry again?
Dan Manser with Apple. I participate in ITUR.
Great.
But one of the things we've seen is particularly ESS passive and the sea surface temperature debates that happened at the last WRC. A lot of that was entirely on the industry side saying we want it, rather than some real engineering-based coexistence debates that could be had. And so trying to understand where the truth is and what actually is reality, I think this is hugely important. And so the more information that can inform that, it's just the aggressive nature of some of those debates between the scientific community, the federal community here in the US, and in the industry. When that plays out in the political realm, which you already spoke to, that policy debate is sometimes not looking at some of these technical details in enough detail.
Let me just say that one of the mandates that we have as this NSF funded center is to try to have joint studies as opposed to debates. But getting people at that table is a challenge. And so if that's of interest, we'd be happy to follow up. We've seen some signs from some of the federal agencies that they might be interested in convening at such a table and being more proactive, but that's a delicate walk.
Right. Well, there is a whole U.S. Delegation process for representing the U.S. interests at the ITU. I think that's a huge opportunity for this, because this is not something that's directly reflected there. There are obviously representatives from a lot of the agencies and contractors and consultants that come to that, but
even
this is
before
exciting to
that
see
process, we're trying to figure out how do we tie in.
Yeah.
The other aspect I'll mention is I look at this as developing models like this, for example. We want them online. We want the reference data online. We want, what the computer science world calls frictionless reproducibility, so that it's not just us that can run the model and a specialist that can interpret it. If you want to, at Apple, have your engineers run the model and understand whether they think it's right or not, they can contribute back, bug reports and say, look, we think you didn't do this right, here's a better method. And then, it comes then following with experimental validation of predictions, is you actually have to validate things to understand whether they really reflect reality or not.
Thank you.
So I was just going to, add, I mean, we understand, the timeline with the WRC is challenging, and, but we're committed to looking at scientific coexistence. We also understand that this is not a one and done challenge, right? This is going to continue. And so part of this effort is also the fact that academics have historically not been engaged in the ITU WRC process. And so as part of this flagship, we can help to educate academics, help them, understand the ongoing technical problems and infuse that into their research as they're going forward under this umbrella. And so, some of the things we do, we hope, we can hit the mark and bringing value to the WRC process. And like I said, I think other things have a much longer arc. And so getting the folks in this room and the academics to understand that process and start engaging is also part of the value proposition of that flagship project.
Excellent. Please go ahead.
Yeah, Michael Calabrese, Open Technology Institute in America. So in Flagship 1, and sorry if I missed this, but are you testing against all, in 7.8, all the known federal uses, or just a few
Just
of the
a few.
most prevalent
So
uses?
we're gonna do the most prevalent and open of the federal use cases, in particular SATCOM as a proxy for what's going on. NOAA and NASA, of course, are using these as uplink and downlink frequencies. So that's the most approachable. One of the reasons is that when you get into dealing with DoD signatures, you start to have export control issues potentially. And we have students, it's an open public research endeavor. And so we really have to be solidly in 6.1 versus 6.2 or type research. And because of that, it's much better for us to go out and work with NASA and NOAA and so forth on these projects, even though there's obviously a huge number of the incumbents in this band actually look like DoD SATCOM or DoD, Link 16 or other things. So there's certainly activities in these bands that the incumbents, I think, would love to engage with us. As a center, we have to be careful how we do that type of engagement.
Okay. So, I mean, immensely helpful, of course, those other ones are a big challenge.
Yes, and hopefully everything we do will be really relevant and somewhat transferable. For example, if we look at Wi-Fi versus a SATCOM signal, one of the things I hope to do is we, upconvert Wi-Fi, we show, look, we see it in the in the SATCOM system and it becomes an interference problem at such and such a distance. We can then try a waveform that's a coexistence waveform designed not to interfere. How close can we get? Oh, look, we can get quite a bit closer because we got 10 dB more ejection. You could try a SATCOM waveform in combination with a waveform that is also designed to coexist, and maybe you can get very close. And that's a piece of guidance that could go into the requirements for such a band that might not have been there if you didn't do the demonstration, show the benefit, show that the implementation is not intractable, for example. And with SATCOM it's hard because a lot of the satellites you can't update them once they're up. They're there as long as their life cycle, which can be long. But
Yeah, and then a related follow-up, which I think may overlap a little with what Dan was asking, but you said your timeline will parallel the National Spectrum Strategy study of the same band. If you have findings along the way, will you feed that into
so
the NSS process?
Oh, absolutely. Our overall process, so one of the things our team is going to learn to do is something the astronomers do, which is write memos. And so a memo is not a paper. It doesn't have to be a publishable result. It can be a negative result. It can be some interesting thing that you just got data on and a little bit of interpretation. I'm hoping to have an effort as we go on, and Renee, you're going to like this, which is to try to take some of these things that occur and distill them out into a form that really is for the policy world. Okay, you and I had a conversation about this, and I'm going to take you up on your implicit offer. So be careful what you wish for when you talk to me, I guess, is the message. But nevertheless, I think that, yes, we want to have this go on. And so, yes, there'll be the open availability of things, but I see as results occur, as milestones are met, we're going to break this up into small enough pieces. There will be some interesting waypoints, and those, we will communicate those, yes.
That's great. That should be really useful. Thanks.
Thank you. All right, I think that's enough for open questions. I think now is kind of our discussion time for related and relevant efforts. If people have things they know are going on and want to talk about them or suggest that we engage with different communities, I think this is a chance to raise your hand and be heard. If you guys on the panel up here can have any ideas or suggest that we engage with people, you can be provocative. I'll start calling on people if they don't start talking.
I guess I'll ask the question, right? And I know, Frank, you brought it up, about the opportunities for AI ML at the edge, and I know I think there's a DySPAN session going on, whether it's going on right now or going on today, on that topic. So I know there's some in the room here working on that. I'd like to hear kind of more about what those opportunities look like and how that might get, pulled into the flagship project.
Hi, my name is Miguel Gonzalez. I'm working with a center initiative, the UPRM, University of Puerto Rico.
Mm-hmm.
And one of the efforts that we're trying to tackle is in spectrum sharing is the RFI mitigation for microwave radiometers that work in 20 to 30 gigahertz. And it's interesting that we're focusing on the waveform, and the deep learning models that we are trying to implement are based on autoencoders that, so are deep learning models that can learn pretty well some patterns in specific waveforms. So we are using the waveform of the absorption model for water vapor in order to detect interferences and some anomalies in the data. So we can reconstruct the same input, but without the interference. So it's an interesting approach that we're
All right.
conducting.
So we should engage with Raphael to get in touch with you if we need to? Is that the?
Yes.
All right, very good. Others with comment? Oh, there, over there. Please, go ahead.
Hello, everyone. My name is Shauna Lee. I'm a student at Florida International University. With our project, I've been applying machine learning to create a system that's capable of predicting, the location of a cell tower based off of the data that we fed into it. It's a classification model that's capable of like understanding patterns within like data like the RSSI, RSRQ, and it like it analyzes those inputs and outputs a prediction of a possible cell tower.
Awesome. So who should I contact with? Is it Deidre should I talk to for that, or? Yeah?
Yes.
Yeah, awesome. So you know, our internal structure for this is not to silo. We're gonna have kind of work element leads for the various areas. And you know, I think that engaging with the AI/ML portion of our center team would be a great thing to do, because reference algorithms and approaches are really important, and especially if we can, you know, make those available as part of, here's data, here's an algorithm, now can people do better, right? So the other thing I'll say is I'm certainly looking forward to having student participation with these field units that we want to build in the workshop, and I would love to have, you know, a good contingent, you know, maybe even you from Florida to come up and work with us on these things and be part of the field teams.
Okay, thank you.
I'll just jump in and say that I think there's some cool opportunities to integrate the data that we can collect from, say, smartphones, as well as the data that we can collect from these advanced sensors that scan over wider swaths of spectrum. So I think thinking about that integration at some point, I think, is an important part of the story.
We can maybe get back to global MAPIS in a little bit, but we have some other questions. Danielle?
Okay, so regarding the spectrum sensing with distributed local sensors, so I'm just wondering if you're thinking about the robustness of the system and reliability. So from the perspective of sensors being malfunctioning over time or misbehaving, and I'm kind of speaking from past experience. Actually, I had a big IARPA project on really doing distributed spectrum sensing, and there were all sorts of attacks that they were actually interested in somebody tampering with sensors to the point that, or the sensors are just, you know, you calibrate them, but, you know, temperature or whatever environmental factor you might end up with. So I'm just wondering if there is any, and machine learning can be actually a great tool for that, to understand what's, you know, can we, I mean, we had the enforcement project in the SpectrumX, which was more concerned about understanding, you know, if somebody is emitting signals that, so it seems like when sensing, we're on a receive side, but still I think we should not ignore the fact that what we are measuring might be, so I mean, this is just something that it came up to my mind right now.
I mean, one of the things we are doing for our experiments is these are platforms that will have teams associated with them who will be attending them effectively. And yeah, they can sit, maybe they'll be having a pizza while the thing sits there and emits signals or collects data for the particular block of the experiment.
No, I'm just thinking long term,
or you're thinking
right?
longer
Like, you
term,
know,
okay.
this is something that obviously we have, this is experiment under our control, right? And we can do these things and make sure everything works well, repeat the experiment and so forth. But I'm just wondering if we go ahead and propose that this is a valuable tool for the policymakers, I think we should be thinking ahead of, like, what does it mean to make it, you know, robust and secure, actually.
Yeah.
And that's kind of additional angle where machine learning, you know, in addition to all the data that you're going to process and infer, can also tell us, you know what, this data doesn't look right. And with a massive number of sensors, right, we can maybe afford that some of them are actually misbehaving while still being robust.
I don't know, one of you guys have a comment?
Well, I was just going to point out that Arup from Idaho National Lab brought up this issue of the cybersecurity of the sensing system and the spectrum management system yesterday. So there's a theme there that we might want to pull on.
I mean, there is a security, and there is also, okay, fine, we're going to make it low cost, and we're going to understand that eventually some sensors will, you know, miscalibrate over time, or something will happen to them, right? And we want to be going back to fix them, but we have our data and ML pipeline that will try to understand that, okay, these sensors are actually outliers or whatever. So, so it's maybe not security, it's just the fact that, you know, this is something that's low cost and not robust. Anyway.
I mean, low cost doesn't necessarily mean low quality. Ultimately, you have to make it at scale.
But I would say every radio, as you know, Frank, we calibrate all the time. Every experiment I run in the lab, you go through the, your radio might have a noise floor of, certain dB. On a hot day, it might increase, right? It might just by aging or other things, connections being loose. All these things can happen in real world in our experiments. So I think we need to understand also the robustness of it.
Okay,
Yeah.
well, that's an interesting point. Continuous calibration is one part of that, but Al, you had a comment on that, I guess, really quick. And Maria was next, actually, so. Okay, if you got a really quick follow-up.
I had no comment, no, but I was going to, go ahead, if you had a comment on that, please.
No,
She has another question.
So I was going to give a status update of what we're doing on the RFI survey that has an impact on scientific coexistence, if that's appropriate.
Okay, let's go to Maria first then, and then we'll come back to you.
So, hey everyone, Maria from UC Albany in computer science. So I wanted to speak to your question around how AI ML can help, and particularly be integrated with the project. And that jumps off a little bit of Daniela's comment. So I think we have opportunity with collecting data on a somewhat unifying platform to employ some of our prior work in characterizing the fidelity of that data and start collecting or creating AI ML models that sort of self-assess the fidelity of data that sensors provide with respect to what are expectations and continue informing reasonable sensor configuration to meet certain fidelity benchmarks. So these are some directions that we can explore in terms of sanity checks on the data. But I also see some good opportunities later in the pipeline as dealing with student engagement and competitions, and particularly with aspects around visualization and showcasing the utility of the data. As a community, as a center, we've all dabbled with various ways to characterize spectrum or optimize occupancy. We've thought about I started thinking anyways about how we might best visualize or how we might advance visualization and couple that with storytelling as opposed to, oh, here's a trace, it looks pretty, but what's happening in it is less clear, especially not to a non-expert. So starting to couple AI, ML on top of visualization and being able to extract knowledge out of a pretty picture and weaving this into student competitions, as you mentioned, I think, are all opportunities to start expanding from sort of more limited controlled testing of AML applications into now controlled, but closer to the real world scenarios.
Excellent. Okay, let's see. I think Al had his comment next.
Thank you. Yeah, I just want to provide an update for everybody to think about regarding the RFI survey that we're working on that has an impact on the scientific coexistence flagship and the long-term pathway for what that could be, how that also could involve other SpectrumX collaborators as well as affiliates. What we've been embarking on, you could think of as effectively putting a NOAA weather satellite, a passive microwave satellite, on top of a van, on top of a vehicle, on top of a mobile platform, and driving that all around the country and finding out circa 2024 what is the RFI landscape into the passive microwave bands that we use for weather forecasting. And I will parenthetically say that if we did not have the microwave satellites to contribute data to our weather forecasts would be pushed back about 20 years. That's no exaggeration from the standpoint of where we are today, utilizing passive data and how important that data is in the accuracy of the forecast algorithms. So where we stand right now, circa 2024, is we don't know how much we're being interfered with because there is this level of what we call insidious interference into passive microwave systems where you can't distinguish that from a geophysical signature. You can't distinguish it from an atmospheric temperature fluctuation or a water vapor fluctuation or a small amount of precipitation, for instance. And so it's this level of interference we'd like to observe. We can't observe it from the satellites because it's that insidious interference. But if we bring our sensor down to the ground level and drive this around, we can then, if we pick our areas properly, get a handle on just how much could be occurring. And that's an important benchmark, circa 2024. So we're doing that right now, and we're also at the same time developing technology that will mitigate to some extent RFI that's caused by gain compression. So I was talking with my colleagues yesterday regarding gain compression in communication systems. And he was saying that well, he's suffering gain compression at the level of 2 dB. That's pretty bad for a comm system, and that compromises it. Our weather systems suffer gain compression at the level of about 1 milli-dB, about 1,000 times smaller. And so gain compression is a really big deal in making sure that the satellites provide proper, accurate antenna temperatures. Now, what are we doing to effect better mitigation? We're developing a new detection technology based upon coherence that has been shown in the laboratory already to completely cancel gain variations caused by compression, completely cancel gain variations caused by 1 over F drift. That's a pretty big deal in the world of radiometry. That kind of sensor we'll be implementing into this little weather satellite we're going to put on top of the van so that we have hyperspectral digital spectrometry that's able to be calibrated to thermal precision. And this will be a project that we hope to get on the road sometime this summer in the fall.
All right.
It's got a big outreach component too. We are going to be traveling around the country. We're going to be visiting various different SpectrumX collaborators. We're going to be visiting various institutions. I'd like to be able to be visiting high schools. I'd like to be visiting MSIs, et cetera. And at the same time we do these visits, showing what spectral observation is in the microwave range, showing what our satellite radiometers do for us, and taking them on a little drive too, and maybe we'll see some interference. You never know.
Al,
So,
thanks
with
very
that,
much.
I'm going to hand the microphone to the next person.
All right.
But I wanted to give everybody a status update because that's something that I'd like collaboration from our other SpectrumX members and affiliates on.
Right.
So, thank you, Frank.
Do you have a poster?
We have one on Thursday. Yes, we do.
Okay.
All right, there we
Check
go.
out Al's poster.
Now, I will say on the calibration side,
that's right.
some of the techniques Al's developing, let's go over here. Okay, he went there. Some of the techniques he's developing, we're hoping to build into the sensors. So it's you know, this absolute calibration is a fundamental thing about making scientific measurements. So,
Hi everyone, my name is Mukarram and I'm a PhD student at Iowa State University working with the ERA project. So we are actually working on something similar to spectrum awareness, and I feel like one of the biggest challenges in making such like spectrum maps is the data and the sparsity, because so some of the models like have been like existing, like most of the people they use like simulated data to generate these models and then try to train these models. But when we go outside in the real world, there are so many things that are affecting the coverage. The signal strength, for example, like there may be a valley inside the actual, or the terrain is affecting the whole coverage. So how do you think, like how can these models actually, like overcome the effect of this sparsity of the data points? Like how can we overcome this thing, especially in the deep learning models?
I have my approach to this, but Nick, you and Randy and Bert have done a huge amount of work looking at kind of occupancy and distributed heat mapping. And what are your thoughts?
Yeah, we've had 2 PhD students looking at this problem, one from more of a detection and estimation point of view, and another from more of a machine learning point of view. I'd be happy to point you to their theses.
Okay, sure.
So
There's a lot, when you think about more than one sensor, when you think about a network of
Yeah.
sensors, there's
Yeah.
lots of interesting algorithmic questions.
Yeah.
Mike has a comment on this too, I think.
No, not on
Or-
this.
okay.
the next-
My comment is that the way this is handled in geophysical systems is you have background models, and data is used to perturb the background models with formal filtering techniques to create a more optimal estimate with lower variance, but it always falls back to the model. And the difficulty is when your model doesn't include the physics of the real world, then you fall back to something that is misguiding you. But nevertheless, that's how that's handled in formal modeling in general.
And what are some of the open challenges that you think the existing models have?
That's a lot. Let's have a coffee discussion. That's a longer coffee discussion. There's a lot.
And just to make sure, you're from where? Iowa State?
All right.
From ARA. Is it ERA or ARA?
All right. All right.
I always ask that question too. John Chapin, National
Okay,
Science
John.
Foundation. You were asking about relevant work on the spectrum awareness side. Maybe everyone up there is already aware, but I just learned that yesterday NTIA announced NOFO 2. Were you guys tracking that? Yeah, closely. So for those who don't know, so there's a substantial amount of investment going to be going into next generation software-defined radios, which includes situational awareness capabilities that can detect government signals and operation in the FR3 bands. So it seems highly relevant. And but the main thing about that is it's focused on advancing technologies from TRL3 to 5 or 6. So I don't know if anything that you're talking about here is already at TRL3.
Yeah, probably our mobile platforms are close, but not necessarily in the bands that they're wanting. So you have to watch.
I don't think you said it specifically, Frank, but in terms of looking for additional funding to fuel the whole vision, okay? We don't expect to accomplish everything that Frank and the team has put together as a vision in terms of using our NSF funds. We are looking very carefully at the NTIA Public Wireless, what is it again? Public Wireless
Innovation.
Supply Chain
Supply
Innovation
Chain Innovation
Fund.
thing or whatever it is, yeah.
And studying those two different buckets of TRL level and advancements. And then the other one, of course, is there's a lot of money going into these microelectronics commons. So when Frank alluded to chips, we see that as an opportunity as well.
Yeah. Let's see, Mike Honig, you had a comment you wanted to bring up?
I just wanted to raise a general discussion point, which is if we're talking about coexistence in 7 to 8, I think there are two main approaches to this. One is uncoordinated and one is coordinated, right? So uncoordinated, I think, is basically what I've been. A lot of the discussion about sensing and data and so forth, in my mind, is sort of uncoordinated. You put these sensors around, you collect data, and you just try to make the best of it and avoid the incumbent. I think another way to approach this is say, well, how can we coordinate between these two, and what does that involve in terms of changing access rights?
Mm-hmm. All right. And I think we're pretty much at the end of our session. So thank you very much, everyone. I hope this has given you some insight into where we're going at SpectrumX. And if you come to our Thursday morning session, there's going to be kind of a lot more team level inside baseball. And then actually there'll be a bunch of stuff that looks like project management. Hi, we're going to do this, we're going to do that. You guys need to get on board. So there'll be a little bit of self-encouragement, I guess, in that one.
Do we need to provide a glossary of all the acronyms for tomorrow morning?
That is beyond my purview, given this field and DoD overlap and NASA. And there is an online acronym guide. But
breakdown structure.
Yeah, well, no, you guys are professors. You don't do enough project management.
Now.
No, Frank, it's a very light touch project management.
I know. You gotta, you just set them forth and they do great things, right? That's what happens. All right, thank you, everyone. I appreciate your attention.